Let's further define and use the coupling coefficient. That coupling coefficient, that's a way to define the mutual inductance. And then we'll look at an example solving two coupled coils where we know the coupling coefficient. So we know that the mutual inductance must be less than or equal to the geometric mean of the two inductances of the coils that are coupled. So we only can reach that geometric mean if all the magnetic flux from coil 1 is captured in coil 2. The further we are away from the two inductors are from each other, then we know that magnetic field inside a coil or inside an inductor, that's where it's fairly uniform and the strongest. As we move further away from the inductor, that magnetic field decreases significantly. There are means with which that we can increase the coupling even with distance, and we'll look at those further. But in general, just the concept that we cannot have a mutual inductance between two coils that is greater than the geometric mean of the coils themselves. It could be the case, however, that the mutual inductance could be greater than L1 or greater than L2, but it can't be greater than the geometric mean of the two. So again, that coupling coefficient then is defined as that ratio between the mutual inductance and the geometric mean. So our mutual inductance is always less than or equal to the geometric mean. That means that our coupling coefficient must be between 0 and 1. So that's our coupling coefficient. If we know that, then we can find the mutual inductance. If a coil is tightly coupled, it's referred to as tightly coupled, that coupling coefficient K is close to 1. And again, that's if they're physically closer. They're wound or oriented to provide greater common flux between the two. And one way to do that is to have a highly permeable material between the two coils, or connecting the two coils, to provide a concentrated and localized magnetic flux. So let's look at an example here. We have an example of two coupled coils, L1 and L2. We know their inductances. L1 is only 0.4 and L2 is 2.5 henries. So it's, a factor of about 6 times. L2 is a factor about 6 times greater than L1. We know that the coil through I1 is 4 times that of through I2, and we know it specifically. It changes with time at a radiant frequency of 500 radians per second. We're looking at a phase shift of 20 degrees and an amplitude of 20 milliamps. And we want to find the current through I2, electrical current through coil 2 at time t is equal to 0, the voltage across coil 1 at time t is equal to 0, and the total energy stored in this system. Now it looks as though from this diagram that we have an open circuit on the left and an open circuit on the right, but clearly we don't, since we have a current I1 and a current I2. So we might want to draw in the fact that we have something there. And then we can easily enough calculate I2 since it's given to us. All we have to do is plug in for t a 0. So when we plug in for t a 0, we end up with just our cosine of negative 20 degrees. We're looking for I2. It's 4 times, I1 is 4 times I2. So it's I1 divided by 4, or 20 divided by 4 cosine of negative 20 degrees milliamps. And so we can calculate that to be 4.698 milliamps to 4 significant figures. Now make sure you can calculate that, and remembering that we have to put our calculator in degree mode even though this is 500 radians per second. Since we're plugging in t is equal to 0, there's no reason not to just keep our calculator in degree mode. Now, what if we want to find the voltage at t is equal to 0? Well, what is that voltage across L1? That voltage across L1, it's that self-induced voltage, so it's our L1 di1 dt evaluated at t is equal to 0, and then it's going to be plus or minus m di2 dt at t is equal to 0. That's the magnetically induced voltage across V1. So to determine whether it's plus or minus, we see that I2, that's flowing into the dot, so it's going to create a positive voltage reference up here at this dot, so we're going to choose the plus, right? So in fact, it's going to be plus m di2 dt. So we can calculate di1 dt at t equals 0. We're given I1, we're given I2. Those are calculatable. But what about m? What about this mutual inductance here? How are we going to determine that? What we're given is k. We're given the coupling coefficient, right? So since we're given k, we need to solve for m. So m is equal to that coupling coefficient k times the square root of L1 or L2. If you plug that in, you're going to solve for m is equal to 0.6 henries. So we see that m is greater than L1, but it's less than L2. It's 0.6 times the geometric mean. It's just ironic that m is equal to k. K has no units. That's just because 0.4 times 2.5, that's equal to 1, right? And the square root of 1 is equal to 1. So once we do that, we can just do a little bit of math to solve for our to the voltage at t is equal to 0. So when we do that, we solve for our first thing we have to do is solve for m, and then we need to take that first derivative of I1 with respect to time, the first derivative of I2 with respect to time, and again plug in t is equal to 0. So when we do that, we have 0.4 henries times that 20 milliamps for I1. When we take the derivative, we have to pull out the omega, so it's omega, but it's derivative of the cosine, so we have an omega, negative omega times the sine. When we plug in t is equal to 0, we just get sine of negative 20 degrees. And then for m, we use our calculated m, which is 0.6 henries. Our I2 has a amplitude of 5 milliamps. When we take that derivative omega, 500 radians per second, we negate that because the derivative of the cosine is the negative sine, and we get that V1 is negative 4 sine of negative 20 degrees minus 1.5 sine of negative 20 degrees. So the contribution to V1 is much greater still due to its self-induced self-induced voltage than due to the mutually induced voltage, and that's really because our I1 is greater than our I2 by a factor of 4, even though L1 is greater than our mutual induced voltage here. So we can calculate that to be 1.881 volts. Now the next thing we want to do is find the total energy, and again we want to just find that at time t is equal to 0. That total energy is going to be due to the current flowing through I1, so it's going to be, it had to do with our L1, 1/2 L1 I1 of 0 squared, and then we have energy in I2 in L2 due to I2, so the 1/2 L2 I2 squared, and then we have due to the mutual inductance, so we're going to have plus or minus m, but it's going to be I1 of 0 times I2 of 0. We still need those amps squared, so we can recall or look up if we have the opportunity what that energy equation now is for this. It's a transformer, but these these magnetically coupled coils. What we have to decide though, is it plus or minus, right? That's our decision here. Do we have plus or minus I1 times I2? And so again, since we have this current I2 flowing in, it's going to create a positive voltage up here, current I1 flowing into here, creating the positive voltage here. What we end up with is the positive. So we do end up with, we're going to use plus m I1 of 0, I2 of 0. So now that's easily enough to calculate because we're just plugging in. We know I1 of 0 and we know I2 of 0. I2 of 0 we have here. I1 of 0 is just going to be 4 times that. We know L1, we know L2, and we know M. So our decision here was that what we're using is the positive. So when we plug that in, you should check this to make sure that you can come up with the right solution as well. We come up with 152.2 microjoules. Recall when we're squaring the milliamps, we end up with 4.698 squared, but that milliamp 10 to the negative 3 squared is a 10 to the negative 6. So we do end up with microjoules here. So that's our first example. When we checked that, what were the key things we needed to determine? Well, we needed to recall how to do our mesh equations here. So in our check, again, we're just showing these open circuits on the right and the left, but we had to realize that in order to have a current here, this is not open circuit. So if it helps, just draw some generic box in there. So you see, okay, there is in fact a current flowing. We have a closed loop. If it was open loop, we wouldn't, excuse me, if it's open circuited, we wouldn't have an I2. We need to have some electrically induced current on one or the other side of these coils. And then we could calculate that, but then our check was the fact that that's positive, right? So we have our electrically induced voltage across to L1 and our magnetically induced voltage across to L1 due to the change in current in I2, and they're coupled with our our mutual inductance M, where our M was equal to K square root of L1 L2. And then in terms of our total energy, since that's positive, this is going to be positive as well. And then if all we needed to calculate was the total energy, if we didn't want to calculate this voltage across L1 has nothing to do with our solution for energy. All we need for energy is in fact the currents, and we're given the initial currents, so the only thing we needed to calculate there was M. We could have just approached that by plugging in at t is equal to 0, solving for I1 of 0, solving for I2 of 0, and then again making sure we know to use the plus M I1 I2. So that's the example. What I want you to do for practice, you can find this on Blackboard or write it down, but I want you to solve this problem as well, where we have there's two parts of the problem. One where we have both parts of the problem. We have a current being forced through our primary mesh here, IS, and we have a coupling coefficient of K. This happens to have the same inductors in here, but you should solve for what the mutual inductance is. And the first part of the problem has X and Y open circuited. The second part of the problem has X and Y short circuited. So now you're given IS, but you're not given an I2 here. So you're going to solve this problem, these two problems, and you can submit those on Blackboard.